Welding inspection, ensuring quality and safety in welded structures. Welding inspection overview. Welding inspection serves as a critical component in ensuring the safety, reliability, and structural integrity of welded components across industries such as transportation, aerospace, oil and gas, and construction. According to the information provided in the referenced Wikipedia article, the process involves a systematic evaluation of the welding procedure, weld joint characteristics, and verification against predetermined standards to avoid structural failures. These inspections are essential because welded structures often operate under high-stress conditions where defects could lead to catastrophic failures like cracks, leaks, and structural collapses. Modern welding inspection systems employ advanced technologies, such as digital weld cameras and machine vision tools, to allow inspectors to identify defects more efficiently. The significance of welding inspection also lies in its ability to assess weld quality at different stages, before, during, and after welding, to maintain consistent quality control. In engineering contexts, welding inspection plays a crucial role in ensuring reliable performance under operational loads, thus reducing maintenance costs and unforeseen failures. Overall, welding inspection integrates process evaluation, defect identification, documentation, and compliance verification to meet industry standards and enhance operational safety. Historical and industrial context. The historical development of welding inspection traces back to early industrial advancements, where the demand for safe and durable structures began to grow. As cited in the Wikipedia source, while welding itself dates to around 3000 BC, formalized inspection practices emerged prominently during the late 19th and early 20th centuries. This period marked rapid industrialization, increased manufacturing complexity, and a corresponding rise in the need for weld reliability. Early inspection techniques were limited, relying primarily on visual examination without standardized procedures or tools. As new welding processes such as arc welding appeared in the 1880s, inspection requirements became more stringent, leading to the development of inspection codes, guidelines, and professional certification programs. Over time, technological advancements such as machine vision inspection systems and high-definition weld cameras have dramatically improved detection capabilities and quality control. Modern welding inspection is now supported by global standards, engineering disciplines, and specialized training programs, ensuring that inspections meet increasingly sophisticated industrial demands. Inspection categories: visual inspection, non-destructive testing, NDT, methods, destructive testing. Welding inspection methods are broadly categorized into non-destructive testing, NDT, visual inspection, and destructive testing. Non-destructive testing techniques allow inspectors to assess internal and external characteristics of welds without harming the component. Wikipedia highlights NDT methods such as mechanical evaluations for assessing size, shape, and defect absence. Visual inspection remains the most widely used method due to its simplicity, cost-effectiveness, and immediate feedback, making it a cornerstone of welding quality assurance. Destructive testing techniques, including tensile, bend, and impact testing, are typically applied to sample welds to verify process viability and mechanical performance, even though they render the tested samples unusable. Collectively, these categories enable a comprehensive assessment of weld quality and structural integrity, ensuring that welds perform reliably under service conditions. Visual inspection is the simplest yet one of the most critical methods for evaluating weld quality. As referenced from Wikipedia, it serves as an essential first step in quality control, enabling inspectors to detect visible discontinuities such as cracks, undercuts, porosity, and irregular bead shapes. Visual inspection often employs tools like magnifying glasses, weld gauges, and borescopes to enhance detection accuracy. This method is particularly valuable because it can be performed quickly and at low cost, often providing immediate insights into workmanship issues. Although limited to surface defects, visual inspection forms the baseline for determining whether further testing is necessary. Its effectiveness is enhanced by proper lighting, surface preparation, and inspector training, ensuring reliable detection of deviations from specified welding standards. Non-destructive testing, NDT, encompasses a variety of inspection methods designed to assess weld quality without damaging the component. According to sources discussing welding inspection types, NDT includes techniques such as radiographic testing, ultrasonic testing, magnetic particle inspection, and liquid penetrant inspection. These methods allow inspectors to detect internal and surface breaking defects, such as inclusions, voids, or lack of fusion, which might not be visible externally. As highlighted in external references, NDT methods are especially valued for their ability to verify weld integrity while preserving the welded structure. Mechanical evaluations in NDT further help determine whether weld geometry meets design specifications. Engineering professionals rely heavily on NDT because it ensures compliance, enhances reliability, and minimizes operational downtime by preventing unexpected failures. Destructive testing involves physically breaking or sectioning welded samples to evaluate properties such as tensile strength, ductility, toughness, and weld penetration. As indicated in the Wikipedia reference, destructive testing methods include tensile testing, bend testing, and impact testing, and are typically applied on sample welds rather than production components. These tests provide valuable information about weld behavior under load and stress, enabling engineers to validate welding procedures and confirm that welds meet mechanical property requirements. Destructive testing complements NDT by offering deeper insights into material performance, weld fusion quality, and the effects of welding variables. Although the method results in the loss of the tested sample, it remains an essential tool for procedure qualification, research, and failure analysis in engineering practice. Technology and quality considerations, machine vision and modern inspection tools, weld imperfections, standards and codes. Modern welding inspection increasingly incorporates advanced technologies such as machine vision systems and high-definition weld cameras. As described in the Wikipedia article, these tools enhance defect detection capabilities by providing real-time monitoring of the weld pool and arc characteristics. Machine vision software enables automated recognition of imperfections, improved consistency, and integration with digital quality management systems. Engineers benefit from such tools because they reduce human error, allow continuous process monitoring, and facilitate data-driven improvements. These technologies are particularly effective in high-volume or high-precision welding environments, such as robotics-assisted manufacturing and critical infrastructure projects. By combining advanced sensing, imaging, and analysis, machine vision tools represent a significant evolution in welding quality assurance. Weld imperfections can significantly compromise structural integrity, making it essential to recognize and address them promptly. According to additional welding inspection references, common imperfections include cracks, porosity, slag inclusions, and lack of fusion. Cracks represent one of the most severe defects due to their tendency to propagate under stress. Porosity results from trapped gas pockets and can weaken the weld by reducing its effective cross-section. Slag inclusions, often originating from inadequate cleaning or improper technique, create voids that reduce mechanical performance. Lack of fusion occurs when the weld metal fails to properly bond with the base material or previous weld passes. Identifying these imperfections allows inspectors and engineers to assess the severity of defects, determine causes, and take corrective actions, ensuring weld reliability and safety. Engineering disciplines rely on standardized welding codes to ensure uniformity, quality, and compliance across projects. According to referenced guides, key standards include AWSD 1.1 for structural steel welding, ASME Section 9 for boiler and pressure vessel welding, and ISO 3834 for fusion welding quality requirements. These standards provide detailed specifications, qualification procedures, acceptance criteria, and documentation requirements. They guide inspectors, welders, and engineers in establishing consistent procedures, assessing weld quality, and ensuring that safety margins are maintained. Adherence to these codes not only ensures regulatory compliance but also supports risk mitigation, improves reliability, and enhances the overall engineering quality management process. Inspector roles and responsibilities, career path and certification. Welding inspectors play a vital role in maintaining quality and safety throughout the welding process. As indicated in referenced guides, key responsibilities include performing visual inspections, conducting NDT procedures, verifying compliance with welding procedure specifications, WPS, and documenting inspection results. Inspectors must understand applicable codes, standards, and welding symbols to interpret design requirements accurately. Their role bridges welders and engineers by ensuring that welds meet design intent and safety requirements. QA/QC engineers further support the inspection process by overseeing quality systems, ensuring regulatory compliance, and coordinating testing activities. NDT technicians specialize in specific inspection techniques, operating advanced testing equipment to identify internal defects. Together, these roles ensure thorough evaluation and certification of weld quality in engineering projects. Pursuing a career in welding inspection requires specialized training, practical experience, and certification. External references highlight that certifications such as CSWIP Visual Welding Inspector and CSWIP Welding Inspector are widely recognized and often required by employers. These certifications validate an inspector's competence in evaluating weld quality, understanding inspection techniques, and applying relevant standards. Certification bodies also offer specialized pathways, including underwater inspection, coatings inspection, and welding quality coordination. Inspectors often transition into inspection roles after gaining welding experience, as this background provides valuable insight into welding processes and defect formation. Career development may also involve engaging with professional organizations, attending training courses, and staying current with evolving inspection technologies and industry standards. Safety risks in welding inspection, inspection timing. Welding inspection requires awareness of various safety risks inherent in welding environments. According to referenced guides, risks include exposure to intense heat and ultraviolet light, which can cause burns and eye damage. Inspectors must also be aware of hazardous fumes and gases generated during welding, requiring proper ventilation and respiratory protection. Additionally, inspections may occur in challenging environments such as confined spaces, high elevations, underwater sites, or industrial facilities, each presenting unique hazards. Personal protective equipment, PPE, including helmets, gloves, goggles, and fire-resistant clothing, plays a crucial role in mitigating these risks. Safety protocols during inspection ensure not only the protection of workers but also the reliability of inspection results by enabling inspectors to perform evaluations without impairment or environmental interference. Effective welding inspection is conducted at multiple stages: before, during, and after welding. As highlighted in referenced material, pre-weld inspections verify material conditions, joint preparation, electrode selection, and compliance with approved welding procedures. During welding, inspectors monitor parameters such as heat input, weld pass sequencing, environmental conditions, and immediate detection of visible defects. Post-weld inspections focus on identifying discontinuities, verifying dimensional conformity, and confirming mechanical integrity through methods such as visual examination, NDT, or destructive testing on sample welds. Conducting inspections at all three stages enables early detection of issues, minimizes costly rework, maintains process control, and ensures final weld quality meets engineering requirements. This integrated inspection approach is essential for high-reliability applications such as aerospace, oil and gas, and pressure vessel fabrication.